Today's lesson is going to focus on introducing you to magnetism and the concept of electromagnetism. So first we want to talk about what is a field. Well, a field is an area of influence. So we can have gravitational fields where we know, say, the Earth's mass creates a field around it where it causes an attraction of another mass. Then we can have electric fields that surround charged particles and can cause charged particles to experience either repulsive or attractive forces. And the one we're going to focus on today is a magnetic field. And a magnetic field is an area of influence that surrounds a magnet. And then it can exert a force on another magnet if another magnet comes in close proximity to it. So what is magnetism? Well, materials like iron, nickel, and cobalt can be magnetized fairly easily. And we have a scientific theory that models magnetism. And we say that ferromagnetic materials have little dipoles that we pretend are kind of like tiny magnets. And they can all be aligned under the influence of a magnetic field. And if they are aligned, then it causes this material to become magnetized. Soft iron can lose its magnetism fairly quickly, but hard iron keeps it longer. So how do you get rid of magnetism? Well, there's different ways. One, you can drop a magnet and it kind of causes the dipoles to become misaligned. Or you can also heat it. And if you heat it, the same thing. The dipoles tend to become misaligned and the material can lose its magnetism. Now I think you're familiar with these two rules, that opposite magnetic poles will attract. So if I have a north and a south pole, they want to come together. But similar magnetic poles, such as a north and a north, they will repel. So I need you to become familiar with magnetic field lines and the little arrows that show its direction. Here's a bar magnet, and you can see that these blue lines represent the magnetic field lines of influence. And they always, our convention is that they always come out of the north and into the south, outside the magnet. Inside the magnet, it'll be opposite. They're circular, and the closer the lines are together, as here they are and here, the stronger the force, or the stronger the magnetic field. As you move away, the lines will become further apart. And this is the rule we talked about. Outside the magnet, it goes from north to south, or what we call, it always seeks. The arrow seeks the south. It's always looking for the south. And the lines never cross. Here's another depiction of it with compasses. And you can see that little red on the compass points to the magnetic south pole. Okay, so it comes out of the north and into the south. So the red on the compass, which points to a magnetic south, will follow the magnetic field lines. Similarly, in this horseshoe magnet, you can see if you put a compass there, it would always, the red would always seek the south. Here's a description of if we put little iron filings, how they would line up in the magnet. And you can see they show the magnetic field lines. north and north, where they repel, it would look something like this. Two unlike poles are going to look like this. And in grade 12, we get into more depth on that. But for now, as long as you recognize the pattern. Okay, so Earth's magnetic field. Which do you think is Earth's magnetic north? And which do you think is its magnetic south? Look at the way the arrows are pointing. Remember, the arrows are south-seeking, magnetic south-seeking. So that would tell me that this is the magnetic south, and this is the magnetic north, which is counterintuitive, because you usually think of this as the geographic north. But yes, Earth's geographic poles are opposite to its magnetic poles. And to be honest, the Earth's magnetic poles have shifted over the years. And in another 1,000 years, they're expected that they might shift back. And the magnetic south, which is now the magnetic south, might become a magnetic north again. But not in our lifetime. So now we're going to introduce the principle of electromagnetism. And there was a discovery back in the late 1700s that Christian Ørsted discovered that if he ran an electric current through a conductor, it generated a magnetic field around it. Now, this is the first time that really electricity and magnetism became interconnected, or noticed that they became interconnected. So this then came up as the principle of electromagnetism. Whenever an electric current moves through a conductor, a magnetic field is created around the conductor. And the symbol we use for magnetic field is this. It's a little vector, and it looks like a B. It's the Greek letter beta. So you have to know that principle of electromagnetism. Whenever an electric current flows through something, flows through a conductor, you're going to get a magnetic field around it. So now, we have to determine, or we need a rule to determine, which way the magnetic field flows around that conductor. So there is a rule, we call it right-hand rule number 1, for a straight conductor. And what we say is, if you have a current flowing through a straight conductor, then if you put your thumb in the direction of the conventional current flow, not electron flow, then your fingers will point in the direction of the magnetic field. Now that's a little hard to see through the wording, so we have some pictures here. You can see here's our conductor, and we've got current flowing up through that straight conductor. So this thumb is put in the direction of that conventional current flow, and the fingers depict the direction of the magnetic field. Okay, so that's the way it will work. Here's another picture. If you put your thumb on that straight conductor, your fingers will show the direction of the magnetic field. And another example. So now we need some convention. I've called it current convention here, but we actually use it for other things as well. You need to recognize that a dot means we're going to use it to depict something coming out of the page. An X, we're going to use that it's a tail. It's going away from you or into the page. An easy way to remember it, I always remember out is like an O, and that's kind of like an O. So the dot is out, the X is in. So let's do some practice here. There's a dot, and I'm showing that the dot is to depict the current. And you can see here, if you've used your rule, your fingers would be going counterclockwise. So the magnetic field is counterclockwise. Try this one. I'll give you a minute. That's the current. It's going into the page. So your thumb will point in. Which way are your fingers going? Hopefully they're going clockwise. Here's another one. Put your thumb in the direction of that current flow. And do you see that your fingers will point in on the right and out on the left? How about this one? Do you see that your fingers will point out on the right and in on the left? And you could show that with a little dot on the right and an X on the left. Another example. This one is showing your magnetic field loops. So which way is the current? You can see it's going to be out of the page. Now, which way do you think the current is going to flow on this one? Up or down? Well, I put my fingers in that circular loop, and my thumb appears to be going downward. So my current flows downward. Now I'd like you to try this work.